Okay, so we only got here to have a look at the lipids after more than an hour. Good. So same deal once again. Just as we have looked at the carbohydrate. So it's about what's the monomeric unit build the all different types of lipids is one thing that you need to worry about them. And another thing is, okay, then what's the chemical nature of all different type of lipids? If you understood what would be the monomeric unit to build all different lipids, then you can easily understand that's what it generate or it shape up the whole entire chemistry. And the one last thing is, who are they? What kind of famous lipids with some distinct functions are there? To just sort them out is how we can approach them. So basically, they are all going to be hydrophobic because their individual components is something called, for one major group of lipids, something called the fatty acids. Fatty acid is such an individual unit, and three such fatty acids can combine together through one adapter. Like a glycerol is a type of alcohol, and it's here serves as an adapter. So we can think of the electrical, the wallet here unit having three plug in it. So each plug, each code, small code of fatty acid can be plugged in. Then you have one single unit of fat. So that's why I use that the short guy, the comedian short guy, to represent the other day, last week, to represent the lipids, because you can have only so many units. Unlike the case of carbohydrate, you can build hundreds of different individual monomeric units to build a starch or a glycogen. Oh, I forgot mentioning the glycogen. Jeez. Glycogen is very similar to starch. Very similar to starch, but it's made in animal. So once you have an extra carbohydrate, after having huge meal, so you have leftovers inside of your body. So how are you going to store them? Obviously, you don't want to store them in an individual small glucose. So you assemble leftover glucose into starch-like big molecule in your body. Okay. That's glycogen. That's why the structural chemical property is very similar, and also structurally very similar to starch. The only difference is this is kind of an animal version of a starch we can think of. And where can you find such a abundant amount of glycogen in your body? Liver. Liver is your factory, your synthetic factory in your body, liver. So everything is actually, almost everything is made there, like all kinds of different lipids and all kinds of different like components like carbohydrates, glycogens are there. And also in your muscle, you need a lot of this energy reservoir in your muscle. So those energy reservoirs are stored in the form of a glycogen. So those two places, famous, to good place that you can look and find so many or so much glycogen are either liver and your muscle in your body. That's it. That's all we can say about glycogen. And getting back to these lipids. So once again, forgetting about all different confusing things. So this must be an individual unit of a so-called fatty acid. And the reason why all lipids are going to be hydrophobic, non-polar. Take a look at all this chemical structure. All you see is nothing but carbon and hydrogen. There is no room for any polarity being generated because you don't have any such a suspicious component like oxygen or nitrogen or phosphorus. If you have any phosphorus or nitrogen or oxygen here and there, then you get to think about, okay, this guy might be a little bit of polar, but no, you don't want to worry about, because all you see is nothing but carbon and hydrogen. Okay, so that's what this material makes non-polar hydrophobic. So they are going to have a difficult relationship with our watery environment. Okay. And the other thing that you notice is, unlike these two fatty acid, like I said, maximum 3 fatty acid can come and then combine together to hook up this one plug-like things to build. Now we call this as a fat. Okay. But what's going on here? Why this guy have some kind of angle? This two has a very straightforward line, whereas the third guy, this third fatty acid, has some kind of angle, characteristic angle like this. Why? The only difference is this. Do you recognize this? We mentioned this type of things last week. It's a double bond. So covalent bond, but having two electrons are shared at the same time together. Then we draw double line to indicate. So this is a carbon covalent double bond. Okay. And the reason why, whenever you have this double bond between two carbons, then you have some kind of angle generated as this totally changed the dimension and the structure. And it makes, before when carbon has freely have 4 different covalent bonds, it can rotate freely. It's like revolving door. One single carbon can behave as if it's a revolving door, but once you have this double bond, and it puts some constraint, for example, so it all of a sudden changed into some one flat surface. There is no freedom to move freely. So it's fixed, it has some kind of fixed angle. And this angle, for some reason, in nature, this angle always being generated in one directional angle. So the more you have this double bond, you can have as many double bond as you want for the sake of a carbon here. It's just depending on what kind of a chemistry you experience here as a single fatty acid. So it's just a matter of like a luck or anything. So you can have this double bond, but whenever you have, every time you have this double bond, then the angle gets larger and larger. Here, luckily, you have only 2 double bond, so the gap between these has only so much, this much. But if you imagine, like this guy has 3 or 4 more double bond over here, then probably it will become like this, the scorpion's tail. That's the nature of this chemistry. And that's what makes this either fat or oil. If you have more double bond over here, then it becomes oil. And if you don't have, on the other hand, any or very few double bond, then you behave basically as a fat. What's the difference between fat and oil? Then their status at room temperature is the difference between fat and oil. Oils are always liquid at room temperature. Of course, you can, if you try hard, you can freeze oils too, but you have to apply very low temperature. But at room temperature, oils usually exist as in a liquid state. But fats, even at room temperature, fats are what? Solid. So that's the difference. Usually, of course, fats are usually coming from animal source fat, whereas oils are coming from this plant source fat. And there is a reason why. Their metabolism. When they make this fatty acid, plant metabolism, they incorporate so many double bonds, whereas in animal metabolism, they incorporate very few double bonds, almost none. That's why animal fats are solid fats. Plant fats are liquid, like oil, because of this reason. Why? If you ask why this, like having many double bonds would make this property as an oily liquid, then answer is space. Like this angle, this widened angle will take up much more space, much more volume for the same amount of, same weight or same amount of given this fat. That makes this, if you take up, for example, you still have a 3 fatty acid as a single fat, but if your whole space taken up is this much, then you have relatively has much more freedom to move around. You can enjoy huge space, move around. And that's, in physical property, that's the nature of property of liquid. Okay. But solid, rigid, solid, because you have only this much space, there is no room for free movement. That's why it shows you some such solid properties. So that's the only difference. And why then we consider this animal fat as such a bad to our health, whereas this double bond, plenty of double bond containing plants oil as a healthier alternative. Why? Same reason that we just mentioned in the previous session, the atherosclerosis. It can more easily it can clog your blood vessel because it's a solid. So once they stay solid in the room temperature, then it will block the passage of blood. And the biggest risk of such blocking blood vessel is then your whole oxygen transport will be blocked. Then you will die soon. A lot of your body part will die. So that's the problem. So that's why your circulatory system has a problem if you have a larger supply of this animal fat. Other than that, what's wrong? Yeah, there's nothing wrong about this animal fat. I love animal fat, like butter and all meat, and it tastes better. And so, as long as you can avoid such the circulatory system, but in reality, you can't. So that's why. But anyway, so that's the only difference. And so that's what we distinguish, like between saturated fat versus unsaturated fat. Saturated means not having any double bond. Saturated, so it's an animal fat. Saturated, all carbon, the reason why we call them as a saturated fat is all carbon in the fatty acid are having actually engaged every different covalent bond. It's saturated. But unsaturated means a certain carbon is lazy and idling. So instead of focusing on having other covalent bond, they are having, we can have a double bond over here. So unsaturated. Still you have some room. If you really try hard, you can have one more covalent bond with somebody else. Is kind of an indication of you are unsaturated yet. So that's saturated versus unsaturated. So in nature, so many different unsaturated fat exist usually in plant. But strangely, it's very strange in that all these unsaturated fats, they have always unique, unidirectional arrangement of this. How can I? Here. This, when you have this double bond, you have two alternatives. The other neighbors, both other neighbors containing these carbons are your upside. Okay? And so if that was the case, then those two other hydrogen would be placed below of this center of a double bond. Then we call that as a cis configuration. Cis means the same, because carbons are all placed at the same dimension, and hydrogens are also placed on the same side. So cis, sameness. Trans means different. Here, you have another alternative of arranging this double bond in that, just like you are having this hustle dance. So one carbon is this side and the other carbon is pointed to below of the plane, and we call that as a trans double bond. Okay. So this carbon double bond have either cis bond or trans bond. But strangely, always in nature, when enzymes are trying to make this carbon double bond in fatty acid, they always make only this cis configuration. And that is the reason why whenever you have this carbon double bond, you get to increase this angle to widen the gap between two neighboring fatty acid chain. And that's why it became the oily lipids. Okay. So that's inconvenient, right? You heard that, okay, these oils are healthier than like butter, like animal fat. So you want to have a more frequent occasion of consuming this oil-based lipid. But every time, hey, when you try to have this butter spread on your bread, that's tasty and also convenient. Although every time you have to try a little bit of a microwave things to melt them down, but that kind of inconvenience you can stand on. You can. However, if you imagine that you try this oily plant fat and try to have a spread on your butter, it's messy and not good. Yeah, everybody agrees on. So that's why some people developed some alternative product, which is margarine. Margarine is a butter-like, but actually made from plant oil. How do they do that? They kind of cheated that this oily, highly saturated fat try to incorporate some of the hydrogen artificially to reduce the double bond. But they didn't do a perfect job. So instead of having real, natural, unsaturated, butter-like substance, all they could is, their best job was this insertion of hydrogen artificially. They couldn't control which position, unlike the enzyme. So if we ask the natural enzyme to do this, then enzyme will specifically insert all this hydrogen on the one side, the same side, to create this cis configuration fat. However, in our factory system, we couldn't. So their insertion was random. So now we create something called the trans fat. Trans fat, you know what it is. I already showed what kind of a trans fat. This one carbon is up and the other carbon is down is in during this double bond configuration. Somehow, this is kind of an unnecessary, unwanted byproduct during the process of building this margarine-like hydrogenation, we call it. Anyway, so we created this trans fat in food, of course. Margarine is one such thing. And another, lot of oils to we just bake other goodies like donuts and French fries are all based on this trans fat. So a lot of trans fat can come into our system, which is the problem of trans fats are unnatural products. And that actually creates some problem. It's because this trans fat, why? I mean, this is a trans fat. The only difference between this natural fat and this trans fat is just the location of some hydrogen and then carbon. So the angle of this double bond containing fatty acids, that is the only difference, the angle. What does this angle, make any difference? And it does. So what we heard about this trans fat is it is so bad. So even it is much, worse than the animal-based fat, the saturated fat. So you rather actually, if you are going to have this trans fat based or containing food, you rather actually much better off to have this animal fat, like all this animal fat and the butter is what they are saying. Yeah, that's true. Why? Why is this trans fat is so bad? And they say it will cause a lot of serious problem in this blood circulatory system. That's one thing. Another thing is it will cause a lot of problem in your liver metabolism. And the last thing, last but not the least, is also another group, is it will also cause a lot of problem in your defense, the immune system. So there's all kind of a collective disaster you can get from this trans fat. Of course, luckily these days, so everybody is so crying out loud about the danger of trans fat. So the manufacturers had to come up with something. So somehow they declare, in these days actually on the market shelf, if you examine all those suspicious trans fat containing product, they declare zero trans fat or anything, okay? Which is of course a kind of a lie, but at least the message is it got much safer than the past. But still, the danger is out there. But to us, who cares? I'm not a food and food science major or anything, so I don't care about this health benefit or anything. Why? To me, it's more like, why this trans fat is so more problematic than the natural things? And one thing I can guess is this. Yeah, from the clue that I can get, because it causes also problem in the liver and also blood, and the immune system is, of course, when everything is going bad, then your immune system will work up. So that's another issue. But at least the liver and the bloodstream, the common denominator clue. Because these two, liver is the place where these whole lipids must be broken down for metabolism. Okay? And once all those lipids are broken down, then they are being transported through this bloodstream to arrive at all other respective cells and tissues, okay, to have some kind of other purpose or to store them. That's usually, when we have those lipids, that's usually their destiny, okay, fate. But then these two places are going to have a big problem, means they're not properly metabolized, broken down. Liver, why? We can easily anticipate the problem. We learned already the similar lesson in the case of sucralose. It's always the same thing. Slight difference, very slight difference in structure give us such a panic to the enzyme that are responsible for metabolizing those material. In the case of sucrose metabolism, you give them very similar fake sucrose, believing that, hey, it is also same as the sucrose, so do this. And then enzyme refuse. No, it's not. I'm not going to. Okay? Same thing. Hey, it is the same lipid. Hey, what's the difference between these? Same number of carbon and same number of hydrogen? No, but enzyme recognize the difference. This is very, very, very delicate structural differences, because that's basically, to begin with, that's what the enzymes, the magic works. They can recognize very delicate different structure of each different component, molecule, and then very specifically do this metabolism. That's what all different enzymes do. Otherwise, we would have whole chaos without such a very, very discriminative ability of this enzyme for each different shape of a molecule. It's always, once again, another paradigm of shape. Shape matters, really. How it looks like is extremely, extremely important, because it governs, it dictates every different functions, and same here is the case. So probably enzyme, the lipid digesting enzyme, don't know what to do with these guys. So in the liver, they probably accumulate this trans fat. They should have been digested properly, but they simply accumulate because I don't know about these guys. And also they will be spitted out into the blood. Usually this lipid will be in the very smaller, digested, destroyed product to travel through the bloodstream, but this huge chunk of this trans fat will travel, and then easily they can cause the problem of clogging, blood clogging. And so it's just, you can easily guess what kind of problem you would suffer. Another type of lipid is very special type of lipids, which is phospholipids. Instead of having 3 fatty acid, it has only 2 fatty acid chains. It simply looks like it resembles like you have a 3 outlet electric plug, but only you're using 2 plug, and one is you're using something different. Yeah, that one remaining outlet you are plugging in something totally different material is what this phospholipid is about. So basically, if you understood that this phospholipid, which is really, really, really great for our own sake of survival, which is a really great product, is basically same fatty acid structure. So this is basically same as the regular fat, but one outlet is like being diverted into have to combine with something else. Unlike all 3 regular fatty acids are plugged in the case of fat, but in the case of phospholipid, something else. So here, these 2 are regular fatty acid chain. And you have still one more room here, 3 electric plug, but that one plug is moved upward and then doing something else, like this guy is occupying, which is a phosphate. That's why it is called a phospholipid. So phosphate containing lipid. Now the problem is phosphate. This is what the phosphate looks like. What do you see immediately? How many oxygen you have in the phosphate? 4 freaking oxygens are there, so you're going to have a problem. It's going to be polar. Unlike here, these guys were going to be very, very non-polar, hydrophobic. Oops. You guys have just invited a totally different guy, which is extremely hydrophilic here. How are you going to survive this? Totally two opposite guys living together here. Okay. And to make matters worse, this hydrophilic phosphate guy also invite their whole bad friends to house. Hey, come on over my place, buddy. Look, these another hydrophilic guys are usually on top of this phosphate. So that means this area, whatever this area, become expanded and enlarged and takes up chemically speaking, highly hydrophilic area. So it is like a dimension-wise, it is as large as now this hydrophobic area. So you have two totally different chemistry part. One is hydrophilic and the other one is hydrophobic, unlike the case of a regular fat or lipid. All other regular lipids, they are all hydrophobic. Simply, they don't want to get involved in any water business. But this guy's something different. It can. Yeah, I don't have any problem with dealing with water. This guy. So you have this head and tail rule. That's why this structural thing just appears over here to intimidate you. But once you get scared of this chemistry, then you don't have to be scared anymore. So once and for all, you don't have to worry about this thing. To simply explain what's going on over here, and then now you can totally forget about this. From now on, all you have to worry about this is this little less intimidating shape, which is basic structure we love to use in biology to represent any individual phospholipid. So this is a structure of a phospholipid where here the head, round head represent this phosphate containing hydrophilic group. So we call this as a hydrophilic head. And this area, on the other hand, fatty acid chain, hydrophobic, so we usually refer them as a hydrophobic tail. Hydrophilic head and hydrophobic tail is the basic organization of any phospholipids. So this phospholipid, because of that, as a chemical in its chemical property, we call it as an amphiphilic or amphipathic, having both sides, like this guy. The Count Ashura, have you seen? You haven't? Okay. You guys don't know what the Mazinga Z, the cartoons? Oh, shame on you. Okay, so half male and half female, like this characters. So this phospholipid, individual phospholipid, has a half hydrophilic, half hydrophobic nature. We professionally describe that as an amphiphilic nature. Okay, that's it. Now, that's the beginning of the creation of a life form, actually. So consider that you have thousands of phospholipids somehow generated. And then they will somehow gather together. They will stick together, gathered in the water. What's going to happen is this. This unique, peculiar structure we recognize as a phospholipid bilayer is actually the structural basis of a cell membrane. Phospholipid bilayer? What is this? This is a phospholipid bilayer in that, hey, this is an individual phospholipid, but if they were in the water, now you have a problem because this hydrophobic layer will stick together. Why? We have seen the hydrophobic interaction in last week lecture. In the watery environment, that's the best way for them to survive, to stay as the most stable structure, energetically speaking. So this is exactly the hydrophobic interaction. Okay? So they will stick together to avoid the contact with the water. So you don't have to do anything special. They will do spontaneously for themselves. That's a very unique thing. Think of it. This is whole polymeric unit, whatever it is. If we somehow get to observe this so-called phospholipid bilayer consisting of tens of thousands of individual phospholipid units, which is big polymer. So what you see over here is starting from individual unit molecule, they put together themselves to have this polymer. Is it going to be like energy requiring chemical process or energy releasing chemical process? Which one is it? Usually, normally, if you have to generate a big large molecule starting from one individual molecule, then that is going to be what? Energy requiring process, which is non-spontaneous reaction, right? Metabolically speaking. And the other way around is spontaneous, because when you break them down into individual pieces, then usually you get to release the energy stored inside, and so then that is a natural way of doing things, so we call that a spontaneous reaction. And the reason why that is a spontaneous reaction is because it will release the energy and the entropy. Okay? Starting from organized component structure, you scatter them around to increase the degree of disorderliness. That's exactly what this entropy defines. So entropy is increased. But this case is different. Combining this whole individual together into a big polymer of a phospholipid is a spontaneous reaction. You don't need to provide any energy. Why? Because by doing this in the watery environment, this is something very special occasion. It's because outside the surrounding is water, which is polar, and so it will favor the formation of hydrophobic interaction. So you don't worry about providing any motivation by giving them any extra energy. So this is a good thing. If we still believe that life somehow was generated spontaneously from nowhere in the beginning, and this step must have happened. Otherwise, that's impossible. And at least theoretically speaking, it's there. So you can create nice round bilayer. Bilayer means you have one layer of phospholipid and the other outside layer of phospholipid. That's why we call that a lipid bilayer. And easily you can imagine that if you have a long enough lipid bilayer, they will eventually circularize to have this round cell shape, surface-like shape. And that's what scientists believe, that that's the origin of a cell membrane, which can arise spontaneously. The only matter is, like, will you be able to, by doing so, while you are doing, will you be able to capture inside some very important material like your genetic material? If you somehow were able to do that, then now you are going to be able to survive forever, thanks to that your genetic material is capable of replicating and keep doing it, and let's do this cell division. If you somehow, unfortunately, fail to capture while you are forming your cell membrane, you failed to capture any genetic material, then okay, it was fun while it lasted, and then you will be able to survive, live for only something like 30 minutes or 1 hour or even 24 hours. That's it. That's what we believe. Okay, that's what somehow must have happened to give rise to the first type of LUCA-like first prototypical cell. Anyway, so this. So outside, the reason why it can easily do this is outside this phospholipid, the head, hydrophilic head will take care of everything. Okay? Hey guys, you have some problem with dealing with the water? No problemo. I will do this for you. Okay? And inside of a cell also just simply filled with water. That water, I'm going to do this. Hey, it's me, phospholipid. Okay? Don't be a stranger or anything. So that's the beauty of this phospholipid. And depending on the dimension of a phospholipid, you can have this long bilayer. However, you can have a very small unit of such a small mini like phospholipid bilayer, roundish phospholipid bilayer. Then we call that as a liposome. A lot of the beauty product, your cosmetics these days are being marketed like they are based upon this liposome or anything. On TV, on commercial, you get to hear so many times like a liposome containing a lot of those cosmetics, which is good. Why? Why would they market this name, liposome? Whether they truly use this liposome or not is just a different matter, but liposome is what? What kind of benefit you can get by employing this liposome-based thing? For example, in your cosmetics, your sun cream or whatever those facial cream were simply based upon the liposome, what kind of benefit would you? Why they are selling this point to you? To make you buy more of those liposome-based product. This is lipid. Basically, same material, same phospholipid material as your what? Your surface, your cell membrane. So these guys not going to have any big of a problem of penetrating your skins and inside of the cells, which is a huge benefit actually. Let's say you actually have some very good material like collagen or whatever to make you better in appearance or whatever, then you better actually put them in this inside of this liposome so that they can have a much easier penetration so that it can have a work. Otherwise, no matter how much you have actually applied on your skin, they will just simply stay outside of this. And okay, I only mentioned this occasion example in the cosmetics, which as a male, I consider them as a non-important, the secondary of importance. It's just my male bias, okay, forgive me. But the liposome's importance is actually stands out much more in the drug delivery. If you simply pour some of the effective drug, then ask them, okay, swallow this, it will be very good for you, it will cure your disease. But a lot of times those active component, active ingredient of the drug could be hydrophilic. You have a problem. Because those drug components, perhaps those drugs are synthetic version. So your cell membrane don't have any such transporter. You haven't made any such transporter to recognize those new synthetic drug and then allowing import into your system. Well, then, no matter how good, actually effective those drugs are, if they cannot get into your system, the cell, what good is it there? So that's where the drug companies, again, in these days, came up with this liposome as a drug delivery system. Okay, if we have very promising drug, but the problem is that drug is hydrophilic, then let's put them inside of this liposome. Okay. And then give them. And this liposome will easily have a penetration, no problem, to actual inside of your cell, and inside of your cell, this liposome will dissolve, and then now this, whatever it is, will be released. Okay. So that's basically the strategy of using this liposome in the modern drug delivery system. And everybody get vaccination in these days, actually. The vaccine. These days we are using the DNA vaccine. Okay. Where do you think that we just put those DNA vaccine? Inside of this liposome. Okay. Otherwise, DNA, whatever it is, or RNA, whatever, the Moderna or whatever the Pfizer vaccine is, instead of DNA, is an RNA. The AstraZeneca is actually a DNA vaccine, and then people still think that AstraZeneca is something very inferior. Same thing, actually. The only difference is those AstraZeneca vaccine, based upon this DNA, has to travel even once they are inside of a cell. This DNA must go inside of your nucleus. One more step. There is another danger that before they arrive at the nucleus, those DNA will be destroyed because our defense system, who are you? This is a foreign DNA, I will clip. A lot of things about it. But in the case of RNA, they don't have to. The RNA metabolism stays outside of a nucleus. So once they are inside of this cell, that's all that matters. Then they can start working on as an RNA. So that's the actually very clever point of thinking of this RNA-based vaccine. Right? So that is the reason why they are so new idea about, well, why did I just come up to even just the vaccine story? Sorry. Okay, whatever. So those are those hydrophilic. DNA and RNAs are extremely hydrophilic because they are basically a whole bunch of phosphate containing individual unit. Did you see the phosphate on the phospholipid layer? That is really hydrophilic molecule. So this DNA, RNAs are all extremely hydrophilic, and they better be wrapped inside of this kind of lipid containing molecule before they can get into our system. On the other hand, what if you have some lipid-based drugs and you're worried about that drug must travel through your blood, just like you inject some of the drug through this needle to your one of the blood vessel. Then you have another opposite problem. Those lipids are not going to make the very good travel case in your liquid, the water-based blood. In that case, once again, use this liposome. But instead of putting them inside, this is water environment, they slide in between these two phospholipids so that this area is a hydrophobic layer. So they will be easily inserted over here. And then, so they will easily travel inside your system until they get into the target destination. So, yeah. Oh, cholesterol is still there. I have already talked majority of the cholesterol story in the first session. But anyway, the reason why we still need a cholesterol is not because of this. Of course, yes, cholesterol is the starting material for making very important steroid hormone like estrogen or testosterone or any other cholesterol-based hormone. Okay, glucocorticoid is another cholesterol-based hormone. You don't have to, put the name in your poor brain. Who cares about the name? So this is a precursor of a steroid hormone. Means if you ever want to synthesize in your body any type of a steroid hormone, then you have to start from the cholesterol. Okay. All different type of steroid and the cholesterol molecule has a basic core structural unit that you have to start from there. But that's not important issue fine. Yeah, that is still a very important thing. So if you don't have any this cholesterol, you're not going to be able to make any steroid hormone. So you're not going to be able to show off your true women like or true men like characters or anything else like. That's very important. However, more importantly, it is needed in every different cells of your body. In this way, this is once again, now you can recognize this. Whenever you see it, you can recognize this cell membrane, lipid bilayer. But what are these? Hopefully you can also recognize this unit, unique unit, whenever you see this unit. In chemistry, we call this as a steroid ring structure. So any cholesterol or steroid hormone commonly share this basic unit. So it indicates cholesterol. This is a natural place. The cholesterol's natural place inside of your cell membrane. What business do you have there? Of course, this is also another type of lipid. Okay? So it has no problem of being inserted over here in this hydrophobic layer. Okay? So it can be there. I don't have any problem. But the question is, why are you there? Yes. Every cell has this different amount of this cholesterol. It gives you, the cell membrane, it gives the cell membrane the strength. Like think of a building. You may think this is a building made of concrete. It's a very stable, sturdy, rigid structure. But if you didn't put the steel beam inside of this the concrete building, then that concrete building will be very, very feeble and will collapse easily. And same thing happens here in your cell membrane. Without this kind of a steel beam-like structure giving cholesterol, this cell membrane itself is too weak, structurally speaking. So it cannot provide some kind of a resistance or strength as a one single cell. That sounds like very important function. So without this cholesterol, each cell cannot survive and cannot grow. Far more important than such normal, trivial steroid hormone building things, I guess. And also, by adjusting the amount of embedded cholesterol, you can also control the relative traffic of what kind of a molecule can actually have a pass onto. So that's what it is. So essentially, if you have more cholesterol, you reduce the permeability of the cell membrane. If you have less cholesterol on the cell membrane, you're allowing generally more material to pass easily through. So by doing so, you can actually control how much of those material I will just allow them. Okay. If you need a tighter control, okay, then you put more cholesterol on the cell membrane. So then everybody has a difficulty in getting through. So they complaining about, hey, these guys are so tricky. And some other occasions, okay, I will be easy on you guys, and then reduce the amount of cholesterol, and then those guys outside or inside can have a much better traffic. So that's another thing. Although basically speaking, whatever they are, basically speaking, they have some kind of packing order depending on who you are, like the easiness of this passing through cell membrane. The top of the list goes to this small gas molecule, like oxygen, carbon dioxide, and nitrogen gas like this. This is a very small component, size-wise, and they don't have any charge. They are non-polar and small, better yet. So they wouldn't have any restriction in passing through across the cell membrane. The second tier of this passing degree of difficulty in passing through the cell membrane is water and glycerol, like small, but still a little bit of a polar, but not too much polar molecule. Water is polar, yes. But we do have some trick actually. Here, I don't want to actually make you too much complicated, but water itself, strictly speaking, if we don't have anything else, water itself will have a still tremendous difficulty in passing through this lipid-based barrier because water is polar enough. And we are not that stupid to reject these water molecules. Water is so important. Okay. So we actually implemented so many special transport channels for water only. Okay. Water can make use of such specialized water transport channels, but later probably we'll get to see that identity. But anyway, because of the reason, water is like glycerol, has a kind of a medium difficulty, so they can usually have no problem in passing through. But look at this, guys. Glucose and sucrose. What did I say about the nature of this carbohydrate? They are polar, hydrophilic. Relatively speaking, glucose and sucrose are small enough. They're not that big. So here we forgot something. Some other much larger molecule and also hydrophilic, and they have no chance. But still, the glucose and sucrose has a really enough problem, large enough problem of passing through. They will all be rejected without some special channel. So they cannot even dream of passing through whole bare membrane. Totally, strictly. If you are thinking of passing through freely without the help of any specialized tunnel or channel, then that must be it only up to this. Below that, forget about it. And a little bit of a surprise might be to these guys. These guys are what? How would you call them? Classify. Ions, right, thank you. They are ions. Are they big? They are very small, tiny. Okay. Especially, where is the hydrogen? Hydrogen is not here. But hydrogen also should be included over here, hydrogen ion. They are very tiny little, size-wise, but they have the most difficult degree of this freedom to pass through. Why? Because they are charged. Right. So, these guys cannot even think of anything else. They must. If you want to have any occasion to bring any ion like a chloride or potassium and sodium or hydrogen, even hydrogen, you better come up with some specialized transporter for each of them. So that's the... Why do I keep walking up like this? Okay, so that's about lipids. Now, briefly, concisely talk about the nucleic acid. Once again, nucleic acid, if you were to define nucleic acid, then you can say about it is a polymer of nucleotide. Huh? What do you mean? That means, okay, if you were to define a fat, then you can say it is a polymer of fatty acid. Get it? If you would define a starch, then you can say it is a polymer of glucose. So, same logic, nucleic acid. How many different kinds of nucleic acid can you name? It sounds like very silly, isn't it? Like if I ask you, how many different kinds of carbohydrates can you name? And then you would look at me like, are you crazy? How many different kinds of lipids can you name? But here I dare ask you how many different kinds of nucleic acid can you name? Huh? 2, yes. You're smart enough not to being fooled by. Yes, there are only 2. kinds of nucleic acid in this occasion, which is DNA and RNA. So that's it. So only these two different kinds of nucleic acid exist in this category, but even that, this category must be maintained separately from the rest of this because it has its own unique property and also functional importance. Okay. So anyway, whether it is an RNA or DNA, it is a polymer of a nucleotide. Nucleotide, which means, oh, this guy is the name. The individual component, nucleotide. Oh, yeah, shoot. I already gave you that. Okay. I know you already knew without this, I know, but. So this is DNA. Why this DNA is so chubby and this RNA is so skinny? Yeah, because it's a two, just like you can easily recognize two different colors. Okay? So like these two snakes having, and this one snake. But whether it is an RNA or DNA, it's just one single nucleotide wise. So we are only talking about this little component, which is a nucleotide with which we are building and we are assembling whole long thread like DNA or RNA. But by just looking at one nucleotide in itself, nucleotide itself consists of three different parts, which is one is sugar, ribose. I asked you to kindly remember the name of this sugar, ribose, right? That is the reason. This ribose sugar is here, okay, to bother you. Or deoxyribose. So you have two different types of sugar depending on who you are. Like if you are a nucleotide that is going to be used in RNA making procedure, then you must only use this ribose sugar. And if you, on the other hand, are going one of these nucleotides that is going to make the DNA, then you must use a slightly different type of sugar, very similar to ribose, but a little bit different, which we call deoxyribose. And all these names actually came from this. The DNA, the reason why we call DNA is deoxyribonucleic acid is the full name. Deoxyribonucleic acid, which means deoxyribose containing nucleic acid is what it is. The RNA, the reason why we call this RNA is a ribonucleic acid, which means ribose containing nucleic acid. It sounds like almost. That's the only difference between RNA and DNA, almost. Okay? And another part we call as a nitrogenous base is because that part contained many nitrogen. That's why we call it as a nitrogenous base. And the reason why we call them as a base, which is the opposite of acid. What's the chemical nature of an acid? Acid is what? Hydrogen. Any component that will give out the hydrogen is an acid. Base is totally opposite guy. Any component that gladly to take up any free hydrogen is base. So if acid release the hydrogen and then the base say thank you and then easily grab that hydrogen is their relationship. And here in reality, in biology, acids are always something that they have already given out the hydrogen. Once you get rid of your hydrogen as an acid, then what kind of status do you observe in terms of this charge? Are they going to be negatively charged or positively charged? Acid. They kicked out hydrogen, ion, plus. One plus is gone. So yourself will become negatively charged. So that's how you recognize any acid in biology system. So you get to see any acid, they are usually already negatively charged because my keep hydrogen, I have already kicked them out. On the other hand, the reason why I'm saying this, on the other hand, base, any base would have been what? Already positively charged because they already took up, grabbed hydrogen ion from the system. So any base, because of its unique property, it would have already picked up the hydrogen ion to become positively charged. So in reality, if you look up, the bases are in biology system, bases are already having one plus sign, is how you can distinguish between base and acid. So sometimes we just use interchangeably. Oh, this is a basic protein, which means they are already positively charged protein, basic. Oh, this is an acidic protein. They are already negatively charged protein, kind of. You don't have to know this in this level of class, but once you move up, no one wants to move up to the biology course anymore, so you don't have to worry about it. But if you take a little more advanced class, then we casually say this, basic protein and acidic protein, blah, blah, blah. That means you just understand as, they are positively and negatively charged protein, or any other component for the same way. Okay, anyway, so that's how, and that's the reason why these components, this area is called the base. Okay, they have already took up hydrogen ion and then usually positively charged area in nature. And the phosphate group, those three. So structure-wise, here. But you don't have to don't even try to memorize or familiarize yourself about any structures. You're not going to succeed in. You will keep forgetting about. Okay. So the only thing is about you have these three components. One is a sugar and the other one is something called the base area, which is actually in reality more complicated than what it is. And another group is a phosphate group. Look at phosphate. You already have two negative charges already as a phosphate. It is already phosphoric acid actually. Phosphate is a phosphoric acid. That's why you have so many negative charges already. And this is area where the reason by which DNA and RNAs are already highly hydrophilic because of that. Because you have every different nucleotide has one of these. That means combine all together, how many negative charges would you expect in one strand of DNA or RNA? Huge, huge, huge. And you also have some kind of a base component over here contributed by. But anyway, for the difference between RNA and DNA, you can easily distinguish the difference between the sugar. Sugar used in the RNA nucleotide has this position, you have oxygen. And this is the real ribose sugar. And this is the original. And this is a variation from this original ribose sugar. In that, you can easily see something is missing here. Oxygen is missing at the same position. And that is the reason why it is called the deoxy. Oxygen is deleted, deoxyribose. So it is a variation from original ribose sugar where you have both of this position, oxygen. But for some reason, this sugar has this one oxygen is missing. So how do we call them? Let's call them as a deoxyribose. And for some reason, the deoxyribose is used in the DNA making nucleotide. And there is one other slight difference in that. So To give you a straightforward answer first, there are only 4 different kinds of nucleotides, both in DNA and RNA. Okay. You have only 4 degrees of freedom to be different. If you want to make, for example, if you want to assemble DNA, long strand of DNA, so how many choices do I have? Oh, sorry, you have only 4 choices. The only trick that you can play is to build your DNA out of 4 different types of nucleotide. Position 1, you pick 1 nucleotide. And position 2, you pick the other nucleotide. And position 3, I want to use 1 nucleotide, the same nucleotide that I used. And position 4, I use another nucleotide. Anyway, you can have only so many variations that you can make. That's it. The same thing is for the RNA too. So for all those different nucleotides can come from only this area here. What kind of basis, chemically speaking, is there, makes what kind of different nucleotides is. Like I said, there are only 4 different types of DNA making nucleotide, which means that, only these 4. Either one of these can attach to this position, and that makes 4 different kinds of nucleotide in DNA. And instead of this, whatever this guy T, we usually abbreviate as a T, its full name is the thymine. In RNA, the thymine is absent, but instead somebody else is taking up the thymine's space, which is this uracil. That's the only difference here. So in the case of RNA making nucleotide, these 4 different nucleotides, the nitrogenous base, make the different kind of nucleotide, whereas in DNA, once again, these 4 different kinds of base make different nucleotides. That's it. And that will make individual component of as a nucleotide. And basically DNA or RNA is a whole assembly of each individual different nucleotide in such a long chain thread. It's like such a long chain in that how many long, in the case of human, how many different individual nucleotides are there in a single human cell? 3.2 billion nucleotide in pairs, which means altogether 64 billion nucleotides are making up our entire DNA in a single human cell. Different organisms also will have a different number of nucleotides. And we casually refer the DNA sequence or anything, DNA sequence. What do you mean by DNA sequence? It's like, let's say in a book, you open the book, and that book sentence is made of whole different kinds of alphabet. Right? And this alphabet has 26 different alphabets in the case of English, of course. Okay? And so if you open the book from page 1 to the last page, then whatever it is, then this is a whole different assembly, different combination of each different alphabets. Same thing here in our gene, DNA, I said there are 64 different nucleotides. But all these 64 different nucleotides, but 4 different kinds of nucleotides. And these 4 different nucleotides, consider them as an alphabet. So here in our case, we have only 4 alphabets, unlike 26 alphabets in the case of English literature. But with only these 4 alphabets, we are doing good. We are doing fine. Same thing, we are doing the same thing. With different combination of these 4 alphabets, we are making some sense. We just generate some book from page 1 to the last page, all of which is contained in small space we call a nucleus. Okay? What do you mean by it makes sense? You read the book, then each some sentence makes sense so that we can have some meaning. Same thing in this whole array of this DNA alphabet, the nuclear alphabet. The way they specifically arranged in combination makes some sense in some cases. That's what we call gene. In terms of what do you mean by making sense? Some combination of this order of nucleotides, somehow by some magic, it generates some specific information of how to make some protein. That's the relationship between gene and the protein. Why do we call them some certain area as a gene? Because that area, just like some sentence or paragraph in our book, that area give you some kind of a meaning. In this case, what kind of protein is going to be made by this? If you're kind of still you can get it, probably wait. Let's wait several weeks for more. Then we can have a better, clear idea about what's the relationship between this DNA and this protein. To give you another kind of a different example is this whole DNA sequence, so to speak, this sequence, arrangement of different nucleotides in orders is just like some whole entire cookbook recipes. So many different dishes. Information is stored there, here and there. Okay. And each of these genes are simply instructions, the recipe of how to make one specific dishes, in this case, one specific protein. And what's RNA? It's a copy of such instruction. DNA is your holy, sacred information, the original, so you don't want to mess so easily around it. So you keep them in a very, very safe place. So whenever you want to do actual real cooking, okay, you get the instruction, the original. You don't want to take your original instruction out of your nucleus. You just keep them in there, and then you make the Xerox copy. So many copies of those same instruction or recipe, and then you bring them down to the actual area of protein synthesis and then give out them to each worker of protein synthesis. Okay, here is how you make the protein. So everyone grab this, and those machine, protein building machine, will get this instruction and read through this instruction one by one. This instruction is nothing but, because later, maybe next week, we are going to get to see, protein is a polymer of amino acid. DNA or RNA is a polymer of nucleotides. On the other hand, the proteins are polymer of amino acids, which means individual amino acids are being assembled to some way and then make some unique protein. Here, in the case of protein, you have 20 different types of amino acids. So you can generate so many divergent variety of different combinations because you have 20 instead of 4. And this relationship is this. This DNA will dictate the order. How to assemble, like let's say you have a protein made of 100 amino acids. Then you have to assign, you have to determine each different, what kind of, at position 1, what kind of amino acid out of 20 will come. At the next position, what kind of amino acid out of different 20 will come. That kind of instruction is already written in your DNA. And that instruction is coming out at you in the form of a copy. That is an RNA. And this RNA is just as good as the original instruction. And who is the one who actually read this instruction and actually assemble this amino acid? Guess what? Something called ribosome is. Okay, sorry, I went too far and it's too late, so I have to stop here. So in the middle of this the nucleic acid discussion, I have to stop and then continue on the rest of the things till next week, but we'll get there. And regardless, have a nice weekend and I'll see you next week.